Hi, welcome back to Proofcast. Today we have a different type of episode. Today I'm going to share my screen. I'm going to install Kontrol, and Palina and Andrei, two of our verification engineers, are going to walk me through how to do formal verification. So if you're a Solidity developer and you know how to use Foundry, you can do formal verification at the end of this video. So in the next 45 minutes, you'll see how to set up the basic structure and how to run proofs. This really is not that complicated, and we would love to get more people using open source developer tooling that were built at RV. So I'm going to go to documentation from our website, and in the installation tabs, you'll find instructions. I'm going to install KUp, which is the package manager, and then we're going to install Kontrol. So I invite you to do this on your own machine, and then you can follow along the entire video. And yeah, let's get formally verifying. So I've installed, this is a fresh Ubuntu system. I've just installed Kontrol this morning. I ran into some issues with my memory. That's why this little window is up here. But increasing the swap file size actually helped, and I was able to install it, and I'm running on a 16 gig system. Palina, I think you told me that we generally recommend 32 gigs for running Kontrol because it is memory intensive. I mean, obviously very powerful software, needs lots of RAM. But yeah, do you guys know of any other maybe common issues that people run into when installing Kontrol, or maybe like there's some tips that you guys have?
Yeah, so as you've mentioned, Paul, we do recommend using a machine that has 32 gigs, but at least 16. Sometimes if the project is too big, so the first step that we have in Kontrol that a user should run at the moment is to run control build to build the project. So to go into a bit of technical details, it runs Forge build under the hood. So building the Foundry project, and then it also applies some additional key focused steps on top of that. And that sometimes causes issues too. It can run out of memory if the project is very big. It can also complain about the size of the project in some other ways. The primary way that we suggest people to use is to install Kontrol via KUp. That is our tool that we have at Runtime Verification that helps install different tools from the ones that we are developing. So yeah, I think the primary issue is that sometimes it takes a bit longer, especially if you're installing it the first time. It gets considerably faster after that. Yeah, it also takes some memory while installing. If that's that, we do distribute Docker images. So every time we release a new version of Kontrol, we publish a new Docker image that you can install. Maybe we can put a link in the comments or something like this in the video description. So you don't, if you don't want to install Kontrol on your system, then it's perfectly fine. You can just use a Docker image, set up a container, and run Kontrol inside this container.
Okay, so I think what we're going to do today is we're going to start with a very simple example, and then we'll try to step it up into maybe more complicated examples. We'll see how that works out. Maybe before we get into it, do you guys want to give us some background on how long have you been working on Kontrol, and how did you get into this role in our team?
Okay, I might go first. So yeah, I've been working on Kontrol, I think, from its inception, basically, which I think it was 2 or 3 years ago when we first had a proof of concept for this. Initially, before that, I was working on the EVM semantics, which is the formal semantics of the Ethereum virtual machine implemented in the K framework. So I've been mostly working on that at Runtime Verification, and I've been implementing hard forks and ensuring that it's up to date. So we've been trying to develop tools on top of the EVM semantics, and at that time, the Foundry framework was becoming more and more popular, so we decided to give it a shot, and we were very optimistic with the results that came out of it.
That's good. That's good. And Palina, how about you?
Right. So I have been working on Kontrol for, I think, almost 2 years now. I have joined when Kontrol was already there, but wasn't its own tool. So that was exciting. Before that, I was doing my PhD, which was also focused on formally verifying smart contracts. So I was developing other tools for smart contract formal verification.
Let's give people some background. So the short version, what is Kontrol and what does it do?
Right. So I would say that, in short, Kontrol, as I've said, is a formal verification tool for Ethereum smart contracts, which means that it's the dev tool, a security tool, that can help you mathematically prove that your code is behaving correctly. So when we talk about formal verification, we need to understand that correctness is always defined with respect to certain specification. And for this specification, we use Foundry tests. So in other words, the user can write some Foundry tests, or maybe have some existing Foundry tests that are fuzzing tests, and just run Kontrol on top of that for additional security guarantees. What it means is that Kontrol helps you check that the test is passing under so-called symbolic inputs, where symbolic essentially means arbitrary, covering all possible values that the input variables can take.
Let's start with the example which we have in our documentation. So let me bring this up.
Yeah,
okay.
So similar to the Foundry framework, there's this option of forge init, which basically creates a new project from the ground up. And I think we also have a similar example for in controls, a similar command. So you can execute control init and the name of the project, and it will create a fresh project from the ground up, and it will automatically add all the dependencies required. So if you notice in the current documentation, there's the first step is to run forge init, and then you have to run forge install and to add this library. But instead, if you choose to run control init and the name of the project, then these two steps are automatically done underneath.
Okay, so do I still have to do forge install and install the cheat codes?
Currently, yes, because you've run forge init first.
Fair enough.
I think you need to enter the control example repository first.
Okay.
The one that was created.
That's what I need you guys here for. I'm a caveman. There we go. And now I would want to, I guess, open a text editor, right? Let's see, control example.
Yeah. Do you have any sort of IDE installed on your system?
I have a cursor.
Mm-hmm. Cursor is essentially a VS Code, right? Yeah, that's going to work. See, and you're calling yourself a caveman.
Well, cursor is what keeps me sane. So, all right. So I guess we want to be in the counter.sol file here, or the test. Well, let's open both, I guess.
Yeah, we do need both to understand what's happening.
This is probably like for you guys, like when I watch my mom try to like do something on the computer, and she's like very slowly moving the mouse before she clicks on something.
Not at all. You're telling yourself really short talk here.
All right, so let's copy and paste this. Right?
Yeah. So just maybe for like tiny bit of context, what exactly why we are suggesting to do this in the documentation. So the contract that was there originally before this copy paste was the contract that corresponds to the Foundry's template. So that's a template project. It's pretty simple. It is a contract that implements a counter. So it has two functions. One allows to set a number to a particular value, and the other is increment. So the flow is you deploy this contract, so you create a new one. Then you set a number to a certain value, and then you can also call increment, and it's going to, like, one is going to be added to the value that was set previously. And by default, the number is 0. So what this project does, if we look at the test file, the counter.t.sol, then we'll see that here they pre-wrote some of the tests for us. This test has the following structure. So first of all, it has the setup function. It's Foundry's convention. So basically, that is the function that gets executed first. It is used to set up the initial state. So we can see here, we are creating a new contract, and we are setting the number to 0. Generally speaking, the number is initialized to 0. Unset integers are initialized to 0 by default, but it is good to make sure that it is initialized explicitly. And then there are 2 tests. So 2 tests are going to be run from the state in which setup ends. So setup is executed first, and then every test is run from the state with which setup resulted in.
And so is it, I'm sorry to interrupt, but this example comes with Foundry, right? This is kind of like the default example they have. Okay, cool. Yeah, sorry, go ahead.
Exactly. Yeah, no, thank you. So 2 tests here. One for test increment calls function increment and asserts that the number is now 1. So it was 0, and then we called the function. It incremented number by 1. It is 1 now. So that is a unit test. It has no inputs. So we're just checking that if we call a function with some concrete, very specific input, the state changes accordingly. It's an important thing to have in your project, but it doesn't provide you with a lot of information about the different behaviors of this code, right? So it doesn't have a very extensive coverage, so to say. And what we can do to improve this, to improve the coverage, we can run a so-called fuzzing test that you can see in line 20, right? You can notice that this test takes an input parameter x, and then the set number function is called with this parameter. That is a parametric test, which means that Foundry, as a fuzzing tool, is going to call this function over and over again for a particular specified number of runs, 256, I think, by default, with randomly generated values of x. And then it checks that with whatever value set number was called with, the number variable is set accordingly. So that is obviously a very efficient technique that everyone should use. But the problem with this approach is that we're still executing exercising a limited number of paths, right? So we are calling this function with different input variables, different input values, but not all of them, right? It's going to take a very long time to enumerate all possible values of unset integers in Solidity. So that's where Kontrol steps in, basically. But what we can do, maybe to run some command, we can run forge test and just make sure that these tests work in the first place, I guess. Maybe that would be useful. Okay.
Oh, well, yeah, because I changed the counter already, right?
Yeah, sorry, my bad. I forgot that is going to have an impact on the compilation. Well, you can...
let's do this. So I reverted to the original doc, and now if I run forge test, there we go.
Yeah, so that is
Cool.
passing, which means the functions are working, right?
Right, but now that we added the second parameter, I guess.
Yeah, so now, and so you'll have to trust me on this, but if we run control on these tests, it's going to pass too. Like, it will tell you that the execution happens as it should. But obviously, there is nothing particularly interested in the original example, right? We're not exercising any paths that are hard to find. Like, no inputs that lead to any issues are hard to generate. So what we want to do here, we want to modify this example to make the issue a bit more obscure, right?
Yeah, so now this is what we're getting at, right?
Yes, exactly. So we're adding a new parameter, and we're adding a revert, which means that the execution is going to fail while it really shouldn't. And in the if condition, so it's going to revert if the new number has this very specific value, and an additional variable in luck is true. So only if both of these conditions are satisfied, then revert is going to be uncovered by the test.
Okay, and why are we adding the in luck? What's the purpose of it?
Just to make it a bit more complicated.
Okay.
Because a combination of both of these variables having specific values is hard to find.
There.
We just want to make Foundry's life a bit more challenging.
Okay, so let's This is the updated test that includes the second parameter. Now save it. And I guess now I can do forge test again, right? And now it should work.
I think you also have to save the counter file. Right.
There we go. You're right. Okay. Yep. It still works. Now can we fuzz this with like, because this is just a unit test. Can we fuzz it and give it different parameters in here, or with Foundry, or no?
So it currently is fuzzed. If you look at the output, you can see that the test set number has been run for 256 runs already. So
Oh, that's fair. Yeah.
It gave 256 different outputs, different inputs to the function, and it couldn't get into the specific branch that reports. You can increase the number of runs by passing -- runs and specify the number of runs that you want to run. And after a given number, probably, I think without the equal, just the space.
Got it. All right. Yep. It ran 1,000 times. Let's do 10,000 times.
Yeah. So eventually it gets the specific input that catches the revert.
Is it random numbers each time, or no? Looks like it fails.
I think that once it identifies a failing path, it would cache that input. So next, if you run it 256 times only, it will still fail because it saves it.
Yep, there you go. Okay, but let's get into the fun stuff. So let's run it with control. So I can go back to the docs. Right, we did this. So we want to build the project with control first, right? We can go in here.
Yes. One piece of advice that I can give.
Yeah.
Oh, probably. Maybe I shouldn't give it. I don't know. So just
Listen, we want to make it easier. The fallback.
Yeah, but then maybe it would feel more natural if we run into this issue first. But I don't think we are running into this issue, so I'll just mention it. Sometimes, so control runs forge build under the hood, and forge test also runs forge build under the hood, so it has already been run. And we're using the same folder for storing compilation artifacts produced by forge build. So sometimes if you're iterating on the proofs in your project and you run both forge test and control proof, it sometimes can be a good idea to run something like forge clean or control clean, which just purges the out folder where the artifacts are stored, just to make sure that all the files are up to date. So forge build should take care of that automatically. Both forge build and control build are set up in a way that they actually identify the changes in the files that have been compiled, in Solidity files such as this one. But control build runs forge build with some parameters because we need a bit of extra information from the compilation. So yeah, just to make sure that you're working with like completely up-to-date files, it might be a good idea to just occasionally run the clean command just to make sure everything is up to date.
Okay. But for now, it's building. I could have done verbose, right, to see what's happening under the hood. But maybe we'll do that for the next one.
Yeah, maybe I can probably voice over the verbose logs that aren't seen here. Just, I don't know. But so as I said, it runs forge build, and then it runs case-specific commands. So I'm not sure, we probably haven't mentioned it yet, but control is based on K framework. So that is also our framework for formal verification and reasoning that we develop at Runtime Verification, and that is essentially the formal foundation for a lot of tools that we are developing. And what we need to do is we need to generate some extra files that makes K able to like work with the smart contracts and reason about their behavior. So that's what we're doing here. First of all, we call forge build. Under the hood, it calls the Solidity compiler, and then we generate this extra K files that we need.
So how come I don't have K installed in my KO packages? How come I don't need to have it installed, rather, I guess, to run control?
I think it's getting pulled when you install control as a control dependency.
Okay.
One exciting feature that we're working with and an improvement working on, is we're going to actually drop the control build command. So it's going to take much less time and also will make it a bit easier to iterate. Because so right now, control build has to be rerun every time that you modify the code. So all the changes from the contracts are getting picked up. But we are actually going to stop making you do this.
Okay. What's the logic behind it? Just to save time, or has the
Yeah, pretty much.
Okay.
Save time, make it easier to iterate, make it easier to not forget to run it if you have modified the code.
Look at this biceps. All right, the project has been built. Let's see what are we doing next. Okay. So now we're going to do formal verification, right? Am I doing it?
Yes.
It's like your child going on the bicycle for the first time.
Maybe we should add a bicycle emoji to that. Oh, but if we have a run-in man, maybe that works too.
All right, so what's happening now?
There are a few things happening. So first of all, we are creating the initial state in which, from which we want to start the execution. So to give a little bit more of context, when we are executing a proof, we are basically creating something like a control flow graph of the execution. We call it a KCFG. And the first step is to create the initial node and the target node to which we want to end up. The initial node is pretty general. It's pretty abstract. It has a single account in the state, which is the account of the contract which we want to run. And the target state is also pretty general. I think it only looks for the Foundry success predicate, which basically ensures that no assertion has failed during the execution. And I think another check is at the status code of the execution to ensure that no transaction has reverted. So once this initial state is, once this initial node and terminal node is target node are created, the setup function is executed first. And once that setup function is created, the final state of the setup is basically saved. And then for each proof that's going to be executed next, the final state of the setup is going to be used to create the initial state of the test proof.
Okay, so this was set up, and now it's running test set number. So we expect this to pass as well, right? Because this is just checking that the function works correctly. And then be a third test that we expect to fail.
But do we expect it to pass though?
Look at the test. Oh, right. Okay. Yeah. So are we not running test increment?
No, we're running test set number, if I'm looking at your...
Yeah.
Oh, okay. I see. Yeah, because the setup gets ran automatically, and then we're skipping this one, and we're running this one, and this one we are expecting to fail. Fair enough. I'm following. Just I also don't have that much RAM, so you have to bear with me.
No, I think you're doing great. One thing to note, though, is that the reason we are only executing test set number is because we have provided the option --match--test. And the other way to put it is --empty. And that is also the option you would use in for each test to select a single test run. So we're just trying to be as compatible with Foundry as we can in terms of the interface.
Okay. So, yep, the proof failed. Now, how do I interpret this? Maybe the first question is, what are these nodes? Why is there 24 nodes? And there was...
Right. So nodes are So Andrei has mentioned nodes, right? We're building the initial node, which means the initial state of the contract we are working with and other contracts that are getting deployed in the process of running setup. And then essentially we save these nodes where a node essentially is the snapshot of the state, a snapshot of the network, of the contracts that we are deploying, of the storage of them. And we can also visualize them using a command, but maybe we can get back to that in a second. So what you're looking at with this node 24 is that it just tells us that we got to a certain state that corresponds to this node 24 that we have saved. And in the state, the contract reaches, well, basically the contract reaches a state where some failure happens. And the failure in this case is caused by this revert that happens if x is equal to this magic number and in luck is true. And we do have improvement for the output you're seeing in the pipeline. But the way to interpret it right now is to look at two things. So the first one is path condition that you are actually showing in the screen right now. A bit,
This?
yeah,
No,
in the middle. Yes, this one.
Right?
Yeah,
Okay.
exactly. So essentially what it tells us is that the failure happens if these conditions are true. And these conditions are as follows. X is equal to a certain number. And this number is actually the 0x coffee in hexadecimal.
Mhm.
Confirm that. And also it says that in luck equals 0 is not true. And because in luck is a Boolean, it can be either 0 or 1. 1 corresponds to true. So that essentially says that in luck is true and x is equal to this particular value. That is the requirement for the failure to occur. And based on this information, we also generate a model. Model essentially provides a slightly easier way to interpret the result. You can also build a proof of concept with Foundry based on this. So what it says here is that in luck is 1, which once again is equivalent to being true. X is equal to this value we have just discussed. But we also have the variables timestamp cell and number cell. I don't know, Paul, do you want to make any guesses about what it is?
Well, I guess timestamp would be like the Unix time. Or no? Number cell? I have no clue. I don't even have a guess.
Yeah, fair enough. So generally, Ethereum blockchain and its blocks has the timestamp and the number of the block. So these are.
This is block number. You know what? That would have been my if you gave me enough time, I would have gotten there. I think with my guesses.
Yeah. I trust you. Do you want to re-record that?
No, it's okay.
But yeah, so I'm sure you would have gotten it. Yeah, so Solidity has this globally accessible variables, block.timestamp, block.number. They correspond to the number and the timestamp of the EVM chain at this moment of the block where this transaction is getting mined. So they are symbolic, which means that we assume that they can have almost arbitrary values. They're not fully arbitrary because we know that timestamp probably doesn't make sense to consider infinitely large timestamp because it's unlikely that this formal verification process is reasonable in that case. So we do have some constraints. You can actually see it in the under the remaining implication is. So that contains all constraints that we have on symbolic variables in this process. But yeah, so just to make sure that the analysis is very general, that we are considering all possible executions, which is the goal with formal verification and using control. We assume that block.timestamp and block.number are also symbolic, that they can have a lot of different values, essentially. And these values this could be random, right? Because we have no constraints here on timestamp and block.number. It doesn't matter what value they have. The execution is going to fail if X and in luck have particular values. So that's why we have it in the model.
Okay, and so you mentioned earlier that there's a way to visualize this.
Oh, yes. So we have a command that is called control show. That I think is actually mentioned in the documentation as well. But you can also run control list since it's the first one mentioned in the documentation.
Okay, so setup passed, this failed. Okay. This doesn't give a whole lot of additional information, I suppose, to what we just saw from running the proof.
Well,
True, but yeah, go ahead. Sorry, Andrei.
so the goal of the control is to show you all the proofs that you have in the current project. So currently, because you have executed a single proof, which basically is composed out of the setup function and the test set number, these are the only ones displayed. But in practice, when you have a lot of proofs, list is useful to show the status and to show how many nodes each proofs has.
Okay, and what would happen if I try to prove test increment? Anything interesting or no?
One thing you can notice here is that the setup function has already been skipped, basically, because it reuses the setup from the previous proof.
Yeah, and it was because before it took, I think, a minute 23 seconds, and now it's just instant. And this, theoretically, this is a very easy test, but it's still taking a while.
You can see that in logs, you see that it's starting core server. And that is why it's taken a minute. So at the moment, control cannot really run anything in less than a minute because it just takes a while to start the process that we need to start. So to go into a bit of more technical details, the way control works is it has this interface that is written in Python, if anyone was curious, that interacts with Foundry, and then everything that's related to symbolic execution, the actual process of exploration of different branches, trying to identify if a particular branch is feasible, like if we can get to a certain state, that is done by the backend. And the way control and this backend interact is via an RPC server. So that's what is getting started in a minute.
I've seen this before, right? The KCFG, and I think you mentioned it, Palina, as well. Okay, so if I run this, is that gonna work? Should work, right?
This command probably will not.
Uh-oh. What am I doing wrong?
Do you want to guess? I can stop doing this.
Version 1? Is that the issue?
Yes, it is.
Okay. Do I just get rid of it?
Yeah, or you can say version 0.
Uh-oh.
Yeah, no.
Oh, there we go. We're in. Oh, man. What am I looking at here?
So that is our so-called TUI or terminal UI, I think. So on the left-hand side, you have the nodes, as we have mentioned. So if you click on every node, you're going to see the snapshot of the contracts and the network state. And the thing you're seeing in this window, you're scrolling, that is the key configuration. What you see here is the state of the contract and the network. In the KCL, you see what is getting executed. What are the instructions that are being analyzed at this moment of execution? And these are path conditions, which are constraints that are active at this point of the execution.
Okay, so I think I just kind of ignore the AV0 and just concentrate on what's after that, right? So that's the X.
Yeah, the KV is just a naming convention that we have to show the symbolic values of the function input.
Okay, so I'm looking at this node and the status failed. So are these the failing conditions? Is that right?
So status failed corresponds to the proof. So it has the proof ID, it says the status and the execution time for the proof altogether.
Oh, okay. So this is the whole proof. This is not necessarily the failing conditions. Yeah. Okay.
But you see the status code of this node. So that is node 11, right? You can see that it has it shows what is the program counter at this point, where in the program we are at the moment, the call depth and the status code. So status code is status code, which essentially means that we are not done with the execution. That is not a terminal node where the execution ends, but it also hasn't failed yet. I think that can be interpreted as something like this. When really cool thing that we have right now is working source maps. So there is the SRC thing mentioned next to the node that actually points to the place in the code where this statement is. So you can actually use it to see where in the source code you are. That is a bit challenging because of how compiler works, and sometimes it optimizes things in a way that prevents us from generating the source maps, but usually it points you to the right location, so you can see where exactly it's failing.
Okay, so we're talking about this like line 11 encounter. Yeah. That's all, right? Yeah.
Yes, exactly. But so what you see here is that it starts branching, and it tells you what constraint it is branching on. So essentially, this branch corresponds to, first of all, the check that x is equal to this particular value. And then if that is true, we additionally check if inluck is 0 or 1. And then if you scroll down a bit, you will see that if inluck is 0, then it's not failing. So this branch ends with status code being EVMC success, which means that it finished successfully, all is good. Like
okay,
no
so the whole branch is good. Okay.
Yes, but then we know that if inluck is true, then the failure occurs and the status code is going to change accordingly.
Okay, and then this is the revert. So this is kind of what probably we're interested in, right?
Yeah, exactly.
And is
so
it
by default,
21 or 23? What's the difference between these two? Anyway, they're both revert.
So I think it just essentially takes some time after we identify the revert for the execution to finish. Like there are some instructions after we hit revert that like terminate the execution, basically. And then one thing that you can notice if you scroll a bit up, or you can also scroll down, there might be something interesting too.
What I'm doing now? Down here?
Oh, yeah.
Okay.
Yeah, sorry, I meant the opposite direction, but that's fine. So we do have an output cell. And the output cell tells you what exactly happened, usually. So if it's the result of the execution, something that gets pushed on stack at the end of the execution. And in this case, we are using a custom revert that says something like coffee break. So what we are going to have in the output cell is the hexadecimal value that corresponds to the hash of this custom error. And that is what's essentially telling us what's happening. There it is.
Is it this?
Yeah, so that is not a hash, it's a Python bytes literal, but we do have a way to convert it to hash. We have an option in view KCFG and in control show as well. So here you'll just have to trust me, but I promise it corresponds to coffee break custom error.
Okay. I did clone a repo from a recent audit. Maybe we can spend the last 10 minutes just looking at that, see how that goes. Okay, so I already built this project earlier, so we can save some time on that. Let me maybe open it in the editor. Okay, so this is a real world project, right? And I want to run a proof in 10 minutes or less.
One thing about starting, though, is what I would suggest is to start by looking at foundry.toml file, which configures the Foundry runs, and checking if we have any profiles here that we need to run. So that is sometimes we use a separate profile for control proofs, just so the scope of the compilation for formal verification runs is, for example, the control folder of the tests, like we aren't interested in anything else, but that's not the case here. Let's take a look at control.toml to see how it configures control runs.
There's a lot more stuff in here.
Yeah, so that configures how exactly control build or control proof, for example, commands get executed. And you can see that there are two sections like these things in the square brackets. So the first one is called
build default. Okay, yep.
So build.default suggests that control profile, it configures the run of control build with the default profile. So nothing has to be set. But there are two of them for proof. One is called proof.setup, and the other is called proof.test. So what it means is that people who worked on this set up 2 separate control profiles to run in different circumstances. And if we look at match tests, probably the most interesting thing here, that is almost the last option, we will see that proof that
You're talking about this, or
have a lot of these tests. Yeah, both of them, or either. Proof.setup has only 2 tests that are going to be executed, and they are both setup functions.
So maybe we can start there, because we would have to set it up regardless, right? So let's see how long it takes, and if this is even something we can do in the next 10 minutes. Okay, so control proof is usually what we start with, right? And then I need some help.
Yeah, I'm sure it's the first command we're running, though.
Well, I already did control build.
Okay, sounds good.
Yeah.
Yeah, I'm sorry, Paul, that I keep interviewing you. I don't know why.
No, it's good. I mean, that's what we're here for. So, all right, if I did control build before and I run control build now, it should be pretty fast, right?
It should be. It should be if nothing got modified. But
there we go.
Yeah.
1 second. Okay, so now control proof.
I think you can also do --help and see the help message. I think the option you're looking for should be documented there.
Oh, okay.
There it is. So that one --config profile.
Okay. And then it's, I guess we want to do proof setup. So do I do like this?
I think it's just setup, actually.
Oh, just setup?
Yeah, it reads the command automatically. Like the convention is that command.profile name.
And then do I need anything else? Or it will know to just run these, right? Because that's in the profile. So
everything, everything gets picked up from TOML unless you override this with CLI option.
Okay, so let's try it. Let's see what happens. You're starting a core server. I have a feeling this will take a while. We might have to do another video, but I think this has been helpful.
I did look up in CAS how long this setup takes, and I think it's 3 minutes for one of them and 7 minutes, 25 seconds for the other.
Formal verification is probably not about speed, right? I mean, at some point it is, but
speed does matter if you're running this on CI continuously, which is something we do. So it should be fast enough, I guess, to justify running it every now and then automatically on code updates, which I think probably brings the most value out of it.
And what kind of range in time are we talking about? Like how long does a real world proof take to run on CI? Are we talking about minutes, hours, like days?
I think in previous engagements, we had all of this, like a wide range of proof timings. Usually so I think in one of the recent engagements, which was Lido, we had a proof that took like several days, and then we compressed it to hours, basically. I think the same happened with some of the optimism proofs. So usually we have also pushed a lot of performance improvements to control, which made it possible. I think usually like a couple of hours for a real world serious proofs is actually is something that we see quite often, but it can also be minutes. Like these proofs we're looking at are also real world proofs. That is an actual engagement that we run, that we worked on, and all the proofs are taking less than an hour. Like from what I'm seeing, 40 minutes is the longest one, but there are proofs that take 3 minutes and 4 and something along these lines. Like 20 minutes is also something that I'm seeing here. And they are, as I mentioned, like real world proofs with symbolic inputs, providing a really good coverage.
Okay. That's really helpful. So maybe what I'll do is next time I'll run these in advance so that they kind of execute right away, right? Because the second time you run the same proof, it should be instant, right? Is as long as the code hasn't changed.
Yeah, exactly. But it's also going to show you how long it took previously. So it will still be transparent in that regard.
Nice. Okay. So in a couple of weeks, we'll reconvene. We'll pick up here and see some real world examples. But before you go, I guess we're at time now, but yeah, give me some songs to add to my Spotify. I've made a playlist out of this. Where is it? Here you go. What are we adding?
Oh my God, what did I listen to? I completely forgot about this part. You get me every time.
It's my favorite part.
See. Yeah, I know, it's cool. It's cool as long as I don't have to, come up with something. I really enjoy other people sharing this information. I think I'll go with Little Dark Age by MGMT. I guess that's something I listened to this week.
Oh, Little Dark Age. I like this song. It's already saved in my other playlist. So.
Oh, nice.
Beautiful. Andrei, what do you got for us?
Yeah, I was just browsing my playlist now, and I don't know. I think I would go with from 21 Pilots, Navigating. Yeah.
That's wonderful. 2 more songs. And Andrei, congratulations again. I saw the picture in Slack.
Thank you. Yeah.
All right. So thank you for teaching me a thing or two about Kontrol. These setup functions are still running, so we'll let them run for a couple of weeks. Kidding. And then we'll do this. We'll do this again. I think this is helpful, especially for anybody who's looking to learn how to do formal verification with Kontrol. We would love to hear from you as well. So if you have any questions or if you're running into issues, let us know and we'll try to fix them. Thank you. Thanks for doing this with me, guys. I really appreciate it.
Thank you.
Thank you.
This podcast is for informational purposes only. Views expressed are solely our opinions, not financial advice. Participants may have investments in the projects discussed.